Today we have detection, identification and separation of isotopes. Isotopes are atoms of the same elements but they have different mass. Example, hydrogen can have isotopes of protium, deuterium, tritium. Chlorine have chlorine 35 and 37, and many other elements also have isotopes. Aston's mass spectrometer. Aston's mass spectrograph or spectrometer can be used for this purpose. Actually, this instrument is used for the study of positive rays, but we are using this instrument for our purpose of detection and identification of isotopes. What is the principle behind the instrument, which has been designed by Aston in 1919? By adjusting the applied electric and magnetic field, all the positive ions of same E by M can be brought to same point on a photographic plate. That is the principle, which we can see in detail when we are coming to the experimentation part. Actually, in this experiment, sample needs to be taken in gaseous form, and this gaseous sample is filled in a discharge tube at low pressure. Since gases conduct electricity only at low pressure, under normal pressure they are insulators. So we have to fill a discharge tube with gas at low pressure, and high potential is applied to make them into ionized form. For example, if you take hydrogen gas, on applying high potential they will changes to hydrogen atoms, two hydrogen atoms by the cleavage of the bond between them, and this electron get ionized and H plus ions are formed through this during this process. This can happen in case of any element. The experimentation part can be summarized like this. The rays coming out of the cathode ray tube or discharge tube passed through two slits S1 and S2. Thus formed narrow beam is subjected to electric field using plates E1 and E2. When the electric field is applied, they get deviated from their path and they undergo divergence, or this beam of radiation, beam of positive ions, not radiation, diverged based on their velocity of motion. Then this is passed through a small diaphragm called D. From the D, they directly enter a magnetic field, which is represented by M. And this magnetic field needs to be applied in a direction perpendicular to electric field, which we have already applied using the plates E1 and E2. It again converge the beam into a single point in previous plane. You may have some disturbance when explaining without the diagram. Diagram will come in the next slide. The ions having same E by M meet same point, while the ions with different E by M meet different point in the photographic plate. This is the Aston's mass spectrograph. This is our discharge tube. To this discharge tube we can fill gas through here, and applying high electric potential using anode and cathode, these gases get ionized into positive ions and electrons. These positively charged ions are accelerated towards the cathode since it is negatively charged, and they coming out of the discharge tube through this perforated cathode. Then they are made to pass through two slits S1 and S2. Then we will get a narrow beam of positive rays, and they are subjected to electric field using E1 and E2. On applying the electric field, they get deflected in this direction, and also they diverged or they undergo divergence depending on the velocity of each beam. Through a diaphragm D, they pass and coming to the magnetic field. This magnetic field is applied in a direction perpendicular to electric field. If this is the direction of electric field, it needs to be applied in this direction. On applying magnetic field, they again start to converge to a single point in this photographic plate, which is actually the same plane of this line. So it coming back to the initial plane at a point in photographic plate. Those ions having same E by M ratio will point towards a single point. If they have different E by M, they will point towards the other point. So, depending on the E by M of the ions, they can fall at different points in the photographic plate. For example, you can see the element chlorine. Chlorine has two isotopes, 35 and 37. When they get ionized after the application of high electric potential, we will get two types of ions. One is mass 35 and another is mass 37. It is positively charged. So E by M is 1 by 35 and 1 by 37. If you substitute the value of E 1.6 into 10 raised to minus 19, you will get correct value. For simplicity, we are using 1 by 35 and 1 by 37. So they both will form two lines at two different points in the photographic plate, and also intensity of the line will vary with their relative abundance in nature. If the isotope is rich in the sample, they should have a more intense line. Those who have low abundance will form a line of low intensity. Chlorine isotopes are 35 and 37. They have the mass 35 and 37. Accurately 34.96 and 36.96. When we subject this gaseous sample to ionization and other processes in Aston's mass spectrometer, we will get spectrum like this. Chlorine, we have a line corresponds to 35 and another line corresponds to 37. Two different E by M and two different lines. One is 3 times longer and intense. This actually shows the intensity of the line. So 35 isotope has more intensity than the 37. That means chlorine 35 is 75% and it is 25% in nature. That is why they have different height or they have different intensity. This is the detection of isotopes using mass spectrograph. Now we have to separate isotopes. Separation of isotopes are normally achieved through gaseous diffusion method and thermal diffusion method. According to Graham's law of diffusion, rate is inversely proportional to square root of density. Since density is directly proportional to mass, rate is inversely proportional to square root of mass also, which signifies that when a mixture of lighter and heavier isotopes are allowed to diffuse through a membrane or medium, the lighter isotope moves faster than second one with higher mass. In a mixture of gaseous sample, lighter gas move faster than heavier mass. In experimentation, when a mixture of gaseous sample is allowed to diffuse through a porous barrier into an evacuated chamber, lighter isotopes move faster than heavier one, which leads to partial separation. Complete separation is possible through a cascade system like this. We have a gaseous mixture of two isotopes, say protium and deuterium, or chlorine 35 and 37. If it is protium and deuterium, it is lighter one, it is heavier one. Here we have a mixture of two isotopes in the ratio 1:1, that is 50% protium and 50% deuterium. Lighter isotopes, that means protium, does have a tendency to diffuse to this evacuated chamber more than the heavier one. So they will diffuse to this chamber where this mixture is rich in lighter isotope. So we can imagine that here deuterium is 40 and protium is 60. This heavier isotope tend to concentrate in this region and lighter one in this region. This heavier one again pumped back to this system. Again they diffuses to next chamber. Here again composition changes where lighter isotope become more, 70%, another is 30%. Here also the heavier one pumped to the previous chamber. And in the next step it is 20 and 80. So in each step, as we move forward, in each step concentration of lighter isotope will increase, and if we continue for few more steps like this, we will get 100% lighter isotope and heavier isotope will come back to this region. Successful separation of isotopes of neon, that is neon 20 and neon 22, and also hydrogen H1 and H2 were carried out by Hertz by using a 50 stage system. This kind of 50 chambers needs to be used for the complete separation of them. If the sample is gas, separation is easy. Suppose you have to separate uranium isotopes, uranium 235 and uranium 238. Then they first converted to uranium hexafluoride UF6, which is a volatile compound or which is a gas. This is then subjected to this kind of a diffusion method. Through 4000 stages they can be separated due to their difference in mass. Second method is thermal diffusion method. Principle: when a temperature gradient is or temperature difference is applied to a mixture of two gases, lighter molecule prefer to diffuse towards the region of high temperature, and heavier molecule tend to concentrate at lower temperature region. This is the principle. We have to take a gaseous sample of two isotopes in a glass chamber like this. In this glass chamber, we have a system of passing cold water in the outer region. Using this outer compartment, we can pass the cold water and temperature can be reduced. At the same time, it has an platinum wire at the center which can be heated. So here a temperature gradient can be created by heating this wire. So center of the tube will be at higher temperature and outer region of the glass chamber, which is very close to the water supply system, will be at lower temperature. So outer region is lower temperature and middle region is high temperature. When this gaseous mixture is subjected to or passed through this system, lighter molecules tend to remain in the center part. Why in the central region? They tend to concentrate in the central region because they prefer to move into higher temperature region, while the isotopes with higher mass tend to concentrate in the outer region. They can be collected through this pipe, heavier isotopes, and the isotope in the middle can be separated through this region. So they can be separated into two segments. This is the separation of isotopes by applying temperature difference. In previous method, there is a difference in the density or mass of isotopes, then the isotope with low molecular mass will tend to move towards the evacuated region, or they have a higher tendency to undergo diffusion. Thank you.